So I want to talk a little bit about even and odd functions, and we're going to see the connection to Fourier series at the end of this video. But for now, let's just remind ourselves of the definition of, first of all, an odd function. That's what I've labeled 1 here. The definition is that if we can say f of minus x is always equal to negative f of x. So if I'm trying to sketch an example of an odd function, we could think about, suppose that we knew for positive x values, it looked like this. If it's odd, then for negative x values, it should look like this. That's the idea of taking that kind of symmetry, but flipping it over so that the sign is affected. Now, from this, we can get a clear picture of the consequence of this on integration. So if I were to integrate from minus a to a, we should get equal area but opposite in sign so that it would cancel out. If instead I have an even function, we define that to say that f of minus x is always equal to f of x. So if I were to, again, try to sketch an example of an even function, let's assume again that I know that the value, or f of x looks like this to the right of the y-axis. Well, if I know that f of x is even, then I should have the left side look like this. There should be some symmetry across the y-axis there. Consequently, what we can say is that the area from minus a to 0 should be exactly equal to the area from 0 to a. And that leads to our integral expression below. So the integral from minus a to a is twice the integral from 0 to a. Likewise, I could say it's twice the integral from minus a to 0. So we're going to put these together in a moment, but let's now pause and start to think about what happens when I take a product of functions that are even and or odd. So in this first part here, if f is even and g is even, let's think about the consequence of the function f times g. Well, what we need to do is check our definition. So f times g, what happens if I plug in minus x for that function? I would plug it in everywhere I see x. Because f is even, I can replace f of minus x with f of x. Because g is even, I can replace g of minus x with g of x. So for this product function, we see that plugging in minus x gives us the same thing that we get when we plug in positive x. So this product would likewise be even. If I multiply two odd functions together, again, let's think about the product. We would want to consider what happens to f of minus x times g of minus x. Because f is odd, we can replace f of minus x with negative f of x. Because g is odd, we can replace g of minus x with negative g of x. But notice that those negative signs being multiplied together are going to cancel. And so we actually just get, again, f of x times g of x. So multiplying two odd functions gives us an even function. And then finally, what if one of our functions, in this case f of x, is even, and then the other, g of x, is odd? If we want to decide about the product of these two functions now, we can plug in minus x. Because f of x is even, we can replace f of minus x with f of x. Because g of x is odd, we can replace g of minus x with negative g of x. And so what we end up getting is the negative of what we get when we just plug in x. And this is what it means to be an odd function. So putting this together, let's think about what the consequences are for Fourier series. So I want to think about products of even and odd functions and the result, whether it's even or odd. And then I also want to think about what so far we haven't touched on is this second property in each case, the integral. So what we're seeing here is that if the function I'm trying to find a Fourier series for is odd, then what's going to happen is a sub 0 should be 0, and a sub k should be 0 for all k. Why is that? Well, let's think about those formulas. A sub 0 is the integral, it's 1 over 2 pi, the integral from minus pi to pi of f of x. But if f of x is odd, then we're just integrating an odd function, and that's a direct result of the property we wrote above. a sub k is 1 over pi, the integral from minus pi to pi, of f of x times cosine of kx. Now, remember that cosine is an even function. So cosine of x is, but so is cosine of kx for any k equals 1, 2, 3, etc. And also sine of kx is an odd function. So what I have here is the integral of a product. I'm taking an odd function and I'm multiplying it by an even function. Consequently, this whole product is an odd function. That's what we established above. And again, the integral of an odd function is 0. If instead f of x is even, it's the b sub k coefficients that are all going to be 0 in its Fourier series. To think about that, remember the formula. Let me write it a little bit better. So b sub k is 1 over pi, the integral from minus pi to pi of f of x times sine of kx. Here, we're assuming f is even, but sine is an odd function, and so again, the integrand, which is the product of these two, is itself an odd function. And when we integrate an odd function, we get 0. The purpose of these observations is only as a time saver, so trying to be more efficient. In the previous video, we looked at a process of finding the Fourier series for, let me just write it back down. We were looking at the function f of x that was defined to be minus pi over 2 when negative pi was less than or equal to x less than 0, and positive pi over 2 when 0 is less than or equal to x less than pi. And f of x, we said, is a 2 pi periodic function. So this allowed us to conceive of the graph here, and all I want to do is just sketch it. So the graph, as we saw before, looks like this, and then because we're told that it's 2 pi periodic, we can extend that as far as we need to. So this is the graph of f of x. I mentioned before that I like to always graph the function, and really it comes in here. This function, while maybe it wasn't obvious to me when I'm just looking at the piecewise definition, looking at the graph of it, I can very much tell that from this that f of x is an odd function. And a lot of times that can be much more apparent when looking at the graph. So that's why I highly recommend that, because what we automatically can say is that a sub 0 is 0 and all a sub k's are 0. And if you recall in the previous video, we came to that conclusion, but we had to do some work before we got there, and we could have entirely skipped that integration if we'd taken advantage of this observation. So for future examples, if you do encounter an even or an odd function, it's fine for you to point out that it is even or odd, and then to simply state that consequently we know certain coefficients are 0. And if you don't notice it, you can still get to that answer, but again, trying to think about being as efficient as possible, this is a really useful observation. I will point out, though, that there are functions that are neither even nor odd, and we will encounter those, and in that case, there is no shortcut. We really do have to go through and compute all of our coefficients.